Hi everyone, welcome back to my YouTube channel. So in previous video we learned the DFS approach to arrange the nodes in topological order, and in today's video we will learn the BFS approach to arrange the nodes in topological order. And the BFS algorithm is popularly known as Kahn's algorithm. Just to revise whatever we have studied in the previous videos, a topological sort is a linear ordering of vertices where for every directed edge u to v, if I consider this directed edge 2 to 0, okay, so in a topological order, 2 should always appear before 0, okay. So 2 should always appear before 0 in a topological order, and if I consider another directed edge, for example, for example 2 to 3, then 2 should always appear before 3 in the topological order. Okay, and there's one more thing, one important point, that this only works for directed acyclic graphs. Why? Because in an undirected graph, there is no clear before or after. If I consider an undirected edge between 1 and 2, so there is no clear, there is no clear if 1 appears before 2 or 2 appears before 1, because in an undirected edge we can move from 1 to 2 and also from 2 to 1. Okay, so there is no specified path between 1 and 2, and if a graph contains cycle, you will get stuck in a loop of dependencies where no node can truly come first. Okay, if I consider this graph, okay, one, in order to move to, in order to, 2 depends on 1 and 3 depends on 2 and 1 depends on 3. So you will get stuck in an infinite loop. So therefore, topological sort is not possible for undirected and cyclic graphs. Now, there are two main ingredients that are needed to perform Kahn's algorithm. So, the first one is we need a vector in degree and a Q data structure. Okay, let us first understand what does it mean by in degree of a node. So, to understand the in degree of a node, we need to understand the two types of edges that are possible in a directed graph. So, the first one is incoming edge. So if I consider this directed edge from 2 to 0, okay, by an incoming edge, it means all the edges that are coming from a given node towards a node. Okay, if I consider 0, this edge 2 to 0 is an incoming edge for 2 because this edge is coming from 2 towards 0. Incoming edge means all the edges that are coming towards a particular node. And if I consider the same edge for 2, this edge is an outgoing edge because this particular edge is going away from 2 towards another node. Okay. So incoming edges are those edges that are coming towards a particular node. So for 0, this edge is an incoming edge, and outgoing edges are those edges which are going away from a particular node to a given node. So this edge is an outgoing edge for 2 and incoming edge for 0. So, what does it mean by in degree of a node? So, in degree of a node simply refers to the number of incoming edges for a particular node. If I consider 0, 0 has two incoming edges. One incoming edge is coming from 2 and another incoming edge is coming from 1. Hence, the in degree of 0 is 2. And if I consider 1, 1 has 0 in degree because 1 has 0 incoming edges. So simply the in degree of 1 will be 0. And similarly 2 will also have 0 in degree because as you can see in the graph, 2 has 0 incoming edges. And if I consider 3, 3 has one incoming node or one incoming edge that is coming from 2. And if I consider 4, 4 will also have one in degree because it has only one incoming edge which is coming from 3. And if I consider 5, 5 have two incoming edges. One is coming from 4 and one is coming from 1. So the in degree of 5 will be 2. Now let us understand why do we need a queue data structure here. Okay, as we all know, queue operates on the principle of first in, first out, which means the nodes which will be inserted first in the queue will be taken out first. Okay, so as per Kahn's algorithm, first we will push all the nodes which has 0 in degree in the graph. Why we are going to push all the nodes with 0 in degree in the queue? Because if a node has 0 in degree, it indicates that a particular node does not has any dependencies, does not has any prerequisites. Okay, there is no the current node, the particular node does not depend on any other node, and we can simply start exploring that node. Okay, since 1 and 2 in the graph has 0 integers, we will simply push them inside the queue. Okay, as you can clearly see, 2 has no incoming edge and 1 also has no incoming edge. So it simply indicates both of these nodes does not have any prerequisites. Okay, so we can simply push it inside the queue. Now we will iterate over the queue until queue is empty and will pop nodes from the queue one by one. So the first node would be 1. Okay. Now we will explore the neighboring nodes of 1 and will remove 1 from the graph. Why? Because 1 has already been processed. So we can simply remove it from the graph. Okay. If I remove 1 from the graph, I need to remove the outgoing edges from 1 from the graph. So I need to remove this edge from 1 to 0 and 1 to 5 from the graph. Okay. And why I should remove these edges from the graph? Because it indicates that 1 has already been processed. And if I remove the outgoing edges from 1, it says to its neighbors that you no longer depends on 1. Okay? Since if I am going to remove this edge 1 to 0 from the graph, suppose I removed it. So since I removed the outgoing edge from 1 to 0, I need to reduce the in degree of 0 by 1 because indicates that 0 no longer depends on 1, and as of now it only depends on node 2. So I can reduce the in degree of node 0 by 1. Okay, and similarly if I remove this outgoing edge from 1 to 5, I need to reduce the integer of 5 also, because it indicates that 5 no longer depends on 1 and it only depends on 4 as of now. Okay. Now we have done all the work for 1 and we have processed all of its neighboring nodes. Now we will pop the second node from the queue, that is 2. Okay. Now we will explore the neighboring nodes of 2. So 2 has two neighboring nodes, one is 3 and one is 0. Okay. So we will remove the outgoing edges from 2. So first we will remove this outgoing edge from 2, that is 2 to 0. And in order to remove this outgoing edge, we say to its neighbor that 0, you no longer depends on 2. Okay, that's why we should now reduce the integer of 0 by 1. Now, an important point to note here is that now the integer of 0 has become 0, which indicates that 0 has no dependencies. All the prerequisites of 0 has already been processed. So, we will simply push 0 inside the queue. Because 0 no longer depends on any other node in the graph and we can push it inside the queue. Okay. Now we will remove this outgoing edge from the graph, and in order to remove this directed edge from 2 to 3, we need to reduce the integer of 3 by 0. Now the integer of 3 becomes 0 and we can push it inside the queue because 3 no longer depends on any other node in the graph. So now we have processed all the neighbors of 2. Okay, now we will pop out next element from the queue, which is node 0. As you can clearly see, 0 do not have any neighboring nodes. Okay, so we will simply pop out the next element from the queue, which is 3. Now we will explore the neighboring nodes of 3. So 3 has only one neighboring node and that is 4. We will remove this outgoing edge from the graph, and in order to remove this outgoing edge from the graph, we need to reduce the integer of 4 by 1. So now the integer of 4 also becomes 0, which indicates that 4 no longer depends on any other node in the graph and all the prerequisites of 4 are already processed. So we will simply push 4 inside the queue. Now since we have processed all the neighboring nodes of 3, we will pop the next node from the graph and that is 4. So 4 has only one neighbor and that is 5. So we will remove this outgoing edge from the graph, and in order to reduce this outgoing edge, we need to reduce the integer of 5 by 1. Now the integer of 5 also becomes 0, which indicates 5 no longer depends on any other node in the graph. Now we will simply pop out next node from the queue, that is 5, and 5 does not has any neighboring nodes in the graph does not has any outgoing edges, so we will simply come out of Q. This is our final topological order. We can verify our answer by writing down all the directed edges. If I consider first at 2 to 0, to 2 appears before 0 in our topological order. First edge is verified. If I consider 1 to 0, 1 appears before 0, hence second edge is also verified. Okay, if I consider 2 to 3, 2 appears before 3 in our topological order. Third edge is also verified. If I consider 3 to 4, 3 appears before 4 in this order. This edge is also verified. If I consider 4 to 5, 4 appears before 5 in our final order, and 1 also appears before 5 in our final order.